Every second, the sun bombards our planet with an overwhelming volume of raw energy. But catching that light is only the first problem. This energy is wild, unbound, and completely incompatible with the electrical grid we use to power our lives. To harness this power, we have to trap it at the subatomic level. We do this by taking pure crystalline silicon and injecting it with highly specific impurities, like phosphorus and boron, in a process called doping. This diagram shows the p-n junction. The n-doped side holds electrons, while the p-doped side holds positive holes, forming an internal electric field. Notice the E-field arrow. When a photon strikes, the field rips the newly created electron-hole pair apart, shifting carrier concentrations. This exact mechanism, forcing negative charge to one side and positive to the other, is the photovoltaic effect. It generates the initial voltage required to do useful work. But there is a major catch. This quantum reaction produces direct current, or DC. Nearly every piece of infrastructure in our modern world demands alternating current, or AC. To bridge that gap, DC power flows out of the solar panels, travels through the heavy wiring, and plunges into an industrial grid-tied inverter. This equipment is highly active. Inside that casing, sophisticated microcontrollers run advanced algorithms to continuously monitor the local utility grid. The inverter mathematically sculpts the flat flow of DC energy into a smooth, oscillating sine wave, creating alternating current. But it must fine-tune its output in real time, adjusting the amplitude and phase angle until it exactly matches the utility grid's rhythm. If it misses that synchronization, dumping mismatched power into the network would trigger immediate surges and severely damage the local grid infrastructure. Even with a perfectly synchronized waveform, the inverter is only pushing out between 400 and 690 volts. To move that power over miles of transmission lines without losing most of it to heat, we have to scale the voltage way up. This requires a step-up transformer. This massive piece of hardware acts as the physical bridge to the utility network, elevating the output to transmission levels between 33,000 and 132,000 volts. For large solar plants, engineers rely on a specific configuration known as the Dyne 11 transformer. It functions as a protective firewall between the raw solar farm and the polished national grid. The delta connection traps erratic triplen harmonics so they never reach the grid. The star connection provides a grounded neutral to balance uneven electrical loads caused by cloud shading. Finally, B11 dictates a 30-degree phase shift, perfectly aligning output with utility distribution architectures. The step-up transformer acts as a physical purification filter. By the time electricity leaves this hardware, it is stabilized, standardized, and entirely ready for the grid. Now fully refined, the high-voltage AC surges onto the transmission lines, weaving its way into the national power network. Because this energy matches utility standards perfectly, it enables net metering. The original grid was built to pump power in only one direction, from centralized plants out to consumers. Now, solar facilities and rooftop panels can push excess power backward into that exact same system. Bidirectional smart meters track this exchange. They measure what you pull from the utility and credit you for what you supply, turning the grid into an active two-way marketplace for energy and data. Catching sunlight is only the first step. Generating reliable electricity requires a flawless, real-time translation. Taking a photon at the end of a 150 million kilometer journey, driving it through quantum physics and electromagnetic engineering, and delivering the exact energy powering your screen right now.